Okay, last day of topical review for pre-calc. Day 5, limits, the unit we just finished. We did it virtually. Should be real fresh in your minds. Let's see how we can scoot through this pretty quickly. We have a piecewise function, linear from x is less than 9 to the left of 9, quadratic greater than or equal to 9. Piecewise function, if we're trying to find the limit as x approaches 9, the only way it can happen is if the left-hand limit and the right-hand limit have to equal each other. That's the terminology and that's the mechanics. We don't need to worry about what f of 9 is. It can be point discontinuity, but the left and the right hand have to equal. So when I find the left-hand limit as x approaches 9 from the left, what is the left of 9? That would be this one. 2 times 9 is 18, plus 1 is 19. Right-hand limit, I'm hoping it's 19. Right of 9, that would be that one. 9 squared minus 5. 81 minus 5 is 76. They do not equal. Therefore, what's true? The limit does not exist. What do we got? Jump discontinuity. There's a gap in the graph. All right, next question. Find the limit of that rational function. Obviously, we always, what do we say in our notes? Always direct substitute first, because if it's a continuous function, it's just the function value is the limit. But what happens when we plug in 3? We get 0 over 0, but that does not mean that the limit does not exist. What do we then do? We simplify. Pull out the 2x, x minus 3. X minus 3 on the bottom. We got rid of that bad factor. So now we can plug a 3 into there. 2 times 3 equals 6. So the limit equals 6. And what does that mean? If originally it did not exist, the domain does not include 3, but the limit exists, we got point discontinuity. But the answer to the limit question is 6. Limit as x goes to infinity. What is that also known as? A horizontal asymptote. We had those 3 different options. What do we have here? We have top equals bottom. What does that mean? The limit as x goes to infinity. The other terms take on no meaning whatsoever as x gets larger and larger and larger. The 5x and the 7 are meaningless. So we have the x squared on top and bottom. Take the coefficients. As x gets bigger and bigger and bigger, that function is going to approach 3/5 or 0.6. All right, another one. We have to find the limit as x approaches -6. When plugged in, 0 over 0. Providing evidence, always substitute first. Factor that top. 6 and 2 is 12, plus 6 and a minus 2. X and an x plus 6. Cancel these out. We can now plug that -6 in. Sorry, I've been saying 6. I should have been saying -6. -6 minus 2 over -6 gives you -8 over -6, also known as 8/6, or simplified 4/3. Limit exists even though the function would be undefined. Again, the limit is 4/3. All right, another limit to infinity one. Let's go quickly. Don't look first, look at largest, x squared, coefficients, 4/7. Also known as the location of the horizontal asymptote. A little tricky here. Limit, we did some limit properties. If I broke these apart, the limit as x approaches negative infinity or positive infinity of the first expression, e to the 0.5x, and the limit as x approaches infinity of 8. Remember, the limit of a constant is just a constant. It stays 8. So the question becomes, what is that limit? And as we get bigger and bigger and bigger for x times 5, e to a bigger and bigger number, as x goes to negative infinity, approaches 0. 2 times 0 is 0. So what do we have? We have 0 plus 8. So the whole limit is just 8. If you plug that into your calculator, you would get a decimal fraction, whatever, that's constantly approaching 8. Because again, when that's negative infinity, anything to a negative power is 1 over. 1 over that approaches 0. All right, last one. Limit as x approaches 8 of that thing. -5 log, so let's plug in. -5 log. Again, we can plug in if we want to. If we can, I should say. -5 log of 10. Log base anything of itself is 1. -5 times 1. As x is getting closer and closer to 8, y is getting closer and closer to -5. Okay, let's scoot through these. Actually, you know what? Let's just do 1. We've already done A, we've already done B. Let's look at C as x approaches. Now let's do B. Because what happens? Well, again, let's break them apart. A constant is a constant. What happens, unlike the one above, when it was negative infinity, this is positive infinity. When you raise something to a positive infinity power, as long as it's greater than 1, that gets larger and larger and larger. So that whole thing is going to go to infinity. Infinity at plus 8 is just infinity. And again, if we plug the 6 in, what do we get? We get 6 squared minus 2 times 6 minus 24 all over 6 minus 6. 0 over 0, but that doesn't mean anything. Let's factor. 24 is 6 and 4, minus 6 and a plus 4. They cancel out. I can plug a 6 in now, and I get 10. All right. Enough on limits. Now let's start looking at some graphing. Enough on evaluating limits. Let's put some words next to these. What does each mean? Limit as x approaches 2 is infinity. When the limit is infinity, that's a vertical asymptote. So let's start graphing it as we go. If I made these my axes, that's y, that's x. I've got a vertical asymptote at 2. As x approaches infinity, that looks like a horizontal asymptote, and I'm going to call it negative infinity a horizontal left asymptote at y equals -1. So when I'm over here, I'm going to approach that. X approaches infinity is 4, a horizontal asymptote on the right. Pretty tough to find an equation for this, but we're just graphing it. Is 4, so I'm going to draw a horizontal asymptote over here at 4. And then what's this last one? That's just a point. It's got to pass through the point 3, 7. So at 3, we're up at 7. I got it. So that means we're going to be up above here, approaching the blue vertical, approaching the green horizontal. What happens over here? We're approaching the red vertical, horizontal, and the blue vertical. Doesn't really give us a y-intercept. Looks like mine's somewhere below -1. I like to explain what each of those are before I go graph them. Then it's a whole lot easier to sketch a possible graph of that continuous function. All right, rational functions. To make them into a single rational function, we got to get common denominators, which means we're going to multiply this by one of these. That needs an x, and we're going to multiply the x needs an x plus 3, top and bottom. Now we do a little bit of algebra that we like. 9x times x is 9x squared. -5 times x is -5x. -5 times 3 is -15. All over x squared plus 3x. Now we could maybe pull a x out of the bottom, but we can't really pull anything out of the top, so there is going to be no simplifying. There's the rational function, a single denominator. Okay? And we'd say, what's the limit as x goes to infinity? Well, in other words, the limit as x approaches infinity of c of x. What do we have? A rational function. Degrees are equal. We look at the lead coefficients. That function, as it gets bigger and bigger and bigger, is going to approach 9. All right, we got one more. We're going to multiply the first one. 2 over x minus 2 needs the x plus 2's. 1 over x plus 2 needs the x minus 2's. Let's do some distributing. 2x plus 4. X plus 2x minus 2 is x squared minus 4. Plus x minus 2 over x squared minus 4. Denominators are same, so we can add numerators. 2x plus x, 3x. 4 minus 2 is plus 2 all over x squared minus 4. Identify vertical and horizontal asymptotes. Vertical asymptotes. Limit does not exist. Denominator equal to 0. X squared minus 4 equals 0. Where are the verticals? At x equals 2 and negative 2. Horizontal asymptote, again, limit to infinity. And what do we have? We have a degree of 1 on top. We have a degree of 2 on the bottom. When the bottom is greater than the top, we said the horizontal asymptote is 0. So the horizontal is the x-axis, or y equals 0. All right, looks like we can probably get in one more question. Then we'll have to finish up maybe on another recording. Identify all asymptotes and zeros. Oh, we might be able to go quick. So what do we got? We got r of x equals. We got to do some factoring. Top factors to 2x minus 3, x plus 5. Bottom factors to, sorry, that's a 3. Bottom factors to x minus 7, x plus 5. Before we cancel, just like we said, we have to find discontinuity, or in other words, what's the domain where it's undefined. So domain, x, all reals, except 7 and negative 5. Now we can cancel. The one that cancels out is point discontinuity. The one that remains is infinite discontinuity. So we have a vertical asymptote at x equals 7. Horizontal asymptote, degrees. Sorry, let me do that in green. Horizontal asymptote, degrees are the same. So what do we say? Coefficient 2 over 1, y equals 2. And then our last question is zeros. And just like we waited to find the domain with both bottoms, not 7 or negative 5, the zeros is the numerator equal to 0 of the simplified. We already took care of the 5. The 5 would be point discontinuity. Wasn't asked, so we're not going to address it. So the 0, also known as the root, is just going to set that numerator equal to 0 and solve. Add 3 divided by 2. So it'd cross the x-axis at 3/2 or 1 1/2. Again, if I wanted to go one step further, since we have about a minute, whole or point discontinuity, limit as x approaches 5. If I plug a 5 in on top, pardon me, negative 5. If I plug a negative 5 in on top and a negative 5 in on bottom, if I clean that up, I would get negative 13 over negative 12, which is 13/12, or 1 point something. So where's the whole? Negative 5, comma, 13 over 12. Wasn't asked, but something that we've done. All right, we'll pick up for 2 more examples where we got to write a function, and then we'll have to graph a rational function knowing all of its pieces.